It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farming You a Nice Coffee. Okay, hi guys. Today I'm going to just be hopefully taking you through some calculations for enthalpy. So I'm just going to be doing 6 different examples. Hopefully you'll be able to follow them and it'll help you out a little bit with your calculations. So first what I'm going to do is calculate the energy required to raise 500 ml of water from 21.4 to 56.9. So what I'm going to do is I'm going to leave the calculation or the equation I'm using at the top here, and this first one is just looking at energy. Okay, so we're just going to be calculating the amount of energy that is required to do that. Okay, so if we look at E for energy, all right, it's 4.18 times by change in temperature, which is 35.5. Okay, so if you do your delta T, okay, you do your initial, which is 21.4, you take away 56.9, okay, and you're going to get a delta T of minus 35.5, okay. But for these equations, because we're just calculating the energy required, okay, it's kind of given that it's exothermic, so we don't need to put the negative in, okay. So up the top, we times that by 500. Okay, and when you put that all in, you get a value of 74,195 joules. Okay, so it's really easy to just do these calculations. Okay, hardest part is making sure you've got your volume right. Volume must be in milliliters. Okay, and you just work out your delta T. But because we're just talking about the energy, you can't have negative energy in a sense. Okay, that only comes in when we're actually calculating the enthalpy. So in this case, we're just doing energy, so it's just 74,195 joules. Okay, if you're asked to convert it into kilojoules, divide by 1,000, and you would get 74.2 kilojoules of energy. Okay, if you go on to the next one, here we've got 4.09 grams of potassium hydroxide and 100 ml of water. Initial temperature was 18.5 degrees, final temperature reached was 28.1, calculating molar enthalpy of solution. So this time we're using the enthalpy equation up the top here. So 4.18 times the change in temperature times the volume over 1,000 times the number of moles. So first thing we want to do is calculate our delta T. Okay, and if we do initial take final, we get our delta T of minus 9.6. Now this time it is important, okay, because we're talking about enthalpy, so we want to know that it's a negative value. Okay, our volume of water is 100 mils, so we do delta H is 4.18 times by our change in temperature, which is minus 9.6. So it's important you do that initial take final, because that will give us our negative value for our exothermic reaction, times by our volume, which was 100. Okay, over 1,000 times by the number of moles. Now, number of moles in this case is mass over molar mass. The mass of our potassium hydroxide was 4.09, and the molar mass of potassium hydroxide is 56.107. So if you work those out, you get 0.0729. Put those all into your equation, and you get a value of minus 55.04 kilojoules per mole. Okay, so that's just doing a couple of calculations this time, working out our delta T over here, working out our number of moles. Right, we're doing mass over molar mass, putting them into the equation, getting our enthalpy value here. Negative value, okay, we'd expect this normally to be around about negative 57 kilojoules per mole. Okay, any enthalpy that's an enthalpy of neutralization is about minus 57 kilojoules per mole. This is an enthalpy of solution. Okay. Next one I'm looking at is this one. Okay. So we've got 1.22 grams of glucose. It underwent complete combustion. Now it's important to think about complete combustion because obviously that applies that all of the energy has gone into heating up the water. And there's no energy loss to the surroundings as much as possible, and we haven't lost any energy by doing incomplete combustion. Okay, so here the heat energy released was absorbed by 1,500 milliliters of water. Now be careful about that. Sometimes in the questions they might put 1.5 liters. Got to make sure you convert it. Okay, and a temperature increase of 8.6. So because it's a temperature increase, you've got to remember that your delta T is going to be minus 8.6. So first thing you want to do is calculate your number of moles. So it's again mass over molar mass. So in this case it's 1.22 over our molar mass of glucose, which is 180.15, and that's going to give us a number of moles of 0.00677. Okay, we're going to put that into our equation. Delta H equals 4.18 times by our change in temperature, which is minus 8.6, okay, times by our volume, which was 1500. Okay, we divide that by 1000 times by our number of moles, which is 0.00677. Plug that all in, and you get minus 7,967.8 kilojoules per mole. Okay, you can hopefully see it's really important to make sure you get your delta T sign proper or correct, because if you don't, you won't get your sign correct for your enthalpy value. But this is combustion, so straight away hopefully you're thinking, okay, what I need to actually have is a negative value. Alright, next one I'm going to look at is the molar enthalpy of combustion for butane. So this time we're actually going to turn our equation around a little bit, all right, because they're fairly straightforward to calculate enthalpy of combustion, or enthalpy of solution, or enthalpy of neutralization, whatever it is, given your change in temperature and your volume. So this time what we're going to do is try and calculate the final theoretical temperature. And you had a question like this, I think just the other day. So molar enthalpy of combustion for butane is 2874 kilojoules per mole. Now it's given, because it's an enthalpy of combustion, we don't need to put a negative in there because it's implied. We're burning 1 gram of butane to heat 1 litre of water. So straight away, to have a look, 1 litre, you need to convert that into 1000 millilitres. Initial temperature of 18.5. So that's what we want to start with. Apologies for that. All right. So what we're going to do is we're going to put our equation in. Okay, so instead of writing delta H, I'm just going to be using the equation up the top here. So hopefully you can see as I put them in. So I'm going to put minus 2874. Okay, that's our delta H equals 4.18 times by delta T, that's what I'm trying to work out, times by our volume, okay, which is 1000 milliliters, over 1000 times by the number of moles, which in this case is 0.017. Hopefully you can get that up, put that over on the side. Number of moles equals 1, so 1 gram over the molar mass of butane, which is 58.12. You can double check that that's right. Okay, work out all those values. Okay, start switching your equation around. So delta T equals minus 2874 times by 1000 times by 0.017. So that's just taking this bit down the bottom, okay, putting it up to the other side, and then we're going to divide it by 4.18 times by 1000. Okay, it won't always work out nicely, but in this case the thousands cancel out, so you can just do that calculation. You get a delta T of minus 11.7 degrees Celsius. Okay, now that's your change in temperature, and what the question is asking us to do is the final theoretical temperature. Okay, so if we started with 18.5, we need to add in our change in temperature, which is 11.7, and we're going to get in the end a final theoretical temperature of 30.2 degrees Celsius. All right, now it's theoretical because we're just doing it based on numbers. In theory, in actual practicality, if you do this in the lab, you're probably going to get less than that. All right, because you're going to lose some heat to the surroundings. Some of your butane might evaporate. You might not have complete combustion occurring. All of those sorts of errors. But this is doing a theoretical one, and then you can talk about those errors. Final one I'm going to show you is hexane. Now this has an enthalpy of combustion of minus 4,158 kilojoules per mole, a molar mass of 86.2 grams per mole, and a density of 655 grams per litre. So what we want to do is find the energy density in kilojoules per gram, okay, and then the heat energy released from complete combustion of 2.5 litres of hexane. So this is quite relevant when you're looking at fuels. Okay, so first thing we're going to do is work out the energy density. So all you've got to do is take your enthalpy, 4158, you divide it by your molar mass, which in this case was 86.2, because they give that to us, and so we're going to get a value of 48.24 kilojoules per gram. Okay, so that's our energy density. Now that's important because when you get to the next bit, we're burning 2,500 milliliters, 2.5 liters, okay, and we've got a density of 655 grams per liter. So I actually probably didn't need to do that, sorry, so I'm actually going to get rid of it. All right, so we've got 655 grams per liter. We're burning 2.5 liters, okay, so that works out to be 1,637.5 grams that we're burning. We know that we release 48.24 kilojoules per gram. So if you multiply those together, you can get a value of 78,993 kilojoules of energy. Okay, that is released when we burn 2.5 litres of hexane completely. Okay, so it's important to be able to understand how the density works out, and remembering that to get to your kilojoules per gram, you need to divide by your molar mass up here. Okay, last one. We've got octane, C8H18, very common, most common component of petrol. Enthalpy combustion of 5,754 kilojoules per mole. We want to calculate the mass of octane required to raise 3.6 litres of water by 38.2. Okay, so straight away convert that to 3,600. So again, if we put our values into our equation up here, we've got minus 5754 is equal to 4.18 times by our change in temperature, which was 38.2. Okay, it was a negative value because we raised it. Okay, so those negatives are going to cancel out when we work out our mass, which is important because you can't get a negative mass. Okay, and then what we're going to do is multiply that by our volume, which was 3,600 milliliters. We're going to divide that by 1,000 times n. So in this case, what we're doing is we're actually going to rearrange the equation to work out n. Okay, so n equals, so in this case, when you've got it on the bottom, you flick it over to the other side and you basically swap those two values. Okay, so it's quite straightforward. So 4.18 times by minus 38.2 times by 3,600 divided by 1,000 times by minus 5754. Okay, if you work that out, you'll get a number of moles equal to 0.0999. Okay, so that's calculating number of moles by rearranging your equation. Mass equals number of moles times molar mass. So it's 0.0999 multiplied by your molar mass, which in this case is 114.224. And that will give you a mass of 11.41 grams of octane that was burnt. Okay, so my advice for this video is to go back, rewatch each of them, maybe stop before I start going through each of the examples. Right, you try it yourself and then have a look at how I do it and see if you get the same answer. Okay, other than that, go through your Chem Essentials book, have a look at that as well. Hope this is helpful. Any other equations or any sort of calculations you want me to do, let me know. Thanks guys, see ya.